Okay. Hello, everyone. I hope you guys are doing great. Today, I'm going to talk about all the necessary concepts you need to know before jumping onto the lab 3. So let's start. So lab 3 is all about using an UART, that is Universal Asynchronous Receiver and Transmitter. Or transmitter. It is a piece of computer hardware that translates data between, parallel and serial forms. UARTs are very essential for implementing the serial communication capabilities of a device, allowing it to communicate over a serial port. So here we are trying to communicate between a microcontroller and a computer, that is PC, using the UART, and UART is doing it by connected through a serial port that is RS-232 or USB. So RS-232 or USB, they both are kind of communication protocol, and we don't need to know much about it, but let me tell you some details of what is RS-232. So RS-232 is essentially a long-established technical standard that describes how data is transmitted over serial communication lines between computers and the devices. So here, by devices, I meant the microcontroller. It is, the RS-232 is, it's like a set of rules for how devices talk to each other using serial ports, which was the primary way to connect devices like, for example, we connect our printers, modems, and various equipments to our computers, right? And we want to communicate with those devices. We need to talk with these devices, and we need some protocol, and that protocol is called RS-232, and it is a serial protocol. But nowadays, most of the time we use the USB. That is another protocol, but we're gonna not talk about that here. So the RS-32 is a serial interface protocol. Here, whatever the data sender send, the receiver, the data goes in a serial format. But for different protocols like parallel protocols, so that the data sender sends is going all parallelly to the receiver. So you can think about it that like this is the parallel interface is the fastest way to send the data to the receiver. Our UART acts as the interface between a CPU and a serial port like RS-232. And as I already told you, UART is essential for our applications that requires communication with external devices like sensors, computers, or other microcontrollers. So in our lab, what we are going to do from our computer, we are going to type a character. So basically, we are sending that character to our microcontroller, and based on that condition, the microcontroller, for example, if we send the character R, that is the short form of red, it's gonna blink the red LED. So you can now understand how we are trying to communicate with our microcontroller through this UART device. Now, the question is how we can send the characters or the data using UART. So as I already told you, UART, it passes the data serially, and the maximum data it can send in each clock cycle is 8-bit. But yeah, sometimes it can be like 7 bits or 5 bits, but usually it can pass 8 bits of data serially. And to send the data, we have to tell the UART which segment of our data is actual the data, because we have some other logical bits that helps us to identify any data miscommunication or any error during sending the data. So as a result, we start with a logic low start bit. That's our start bit. Then we pass our data, and then we have sometimes parity bit, and then finally the stop bit. So this is kind of a package we are sending through the UART. And the UART, there's the hardware, when it receives the data, so it try to, understand the data segment, the actual data segment by, differentiating between this among the start and the stop and the other bits. So for example, if we want to send the ASCII letter W, that is 1010111, you can see here we started with the start bit here. Then we have our data for W, that is if we send from LSB to MSB, we have 111, then 0101, and we have the parity bit. And finally, we have the stop bit. So yeah, in some cases, we might not see the parity bit. So what does this parity bit, what is the functionality of this parity bit? Why we are using it? So parity bit is a helper bit used for detecting errors in bits. There are two types of parity checking techniques, like even and the odd techniques. So what the even parity does, for example, say if the total number of ones, let's say I know the total number of ones in our data is a even number, let's say. Now the parity bit value is set to 0 if there are total even number of ones. For odd, it's just the opposite value, right? So for example, here our parity bit is 0 because the number of ones here is odd. So in some cases, as we know, we have odd number of ones, and if we get one here in the parity bit, that means somehow the data got changed during the transmission. So that's why you're using the parity bit for error checking, and we have the stop bit as well. Now let's jump into our code parts of our lab. So in this lab, we'll also get two library program, and inside the library files, we have one function that is called serial setup, that is sar_setup. So in this serial setup, what we have to do, we have we have different registers to control the UART. So as you can see here in table 18.3, table 55, we have a different set of registers. For example, TXDATA, RXDATA, TXCTRL, and RXCTRL, that basically helps us to transmit and control the data over whenever we use the UARTs, right? And each registers are as well as 32 bits here. And now, if you want to transmit the data, we have to first enable the control signal of the transmit control register. So as you can see here, we have here the table 58 for the TXCTRL register. And as you can see here, the bit 0, that is basically for transmit enable. So if we set 1 to this bit 0, that means now the UART knows it's gonna receive something because we are enabling the transmit signal. So now the UART is expecting some data to transmit. Same goes for the receive control register. Bit 0 is for receive enable. So if we set 1 to bit 0, that means we are telling the UART soon you are gonna receive some data because the receive is enabled. We have also the other bits, but that are not useful here for our purpose. But yeah, you can definitely go through the table and understand which bits are doing which kind of operations. So here, what we did in our code, we simply OR the value or we are simply ORing the value of the control register with 1. So here we have the hex 1, that means we have only one bit, that is 1. And if we know from the OR operation, if we have 0 or 1 on any side, and if we do the OR operation with 1, in the output we will get 1. So by doing this this OR operation, we are basically turning or enabling bit 0 from 0 to 1. So that's our serial setup function is doing. Basically, we are enabling the transmit and the receiver control register. Now, we have another function that is the very important function that is serial write. So now we are gonna write some data to the register, and the UART gonna try to transmit the data from that register to the microcontroller. So this function serial write, this function returns nothing, because you can see it starts with the void, and it's taking just 1 byte character, that is C. So what we know that 1 byte is 8 bit, and it's receiving 8 bit of character. And then we initialized a 32-bit unsigned variable, that is register val. Now we have this while condition. So this while condition is continuously checking a condition within this the brace. So here the condition is checking what it's basically an operation. So what we are doing here inside this condition, so we have the register val, and inside the while loop we are accessing the register value from this TXDATA register. So as I already told you, we have total 4 register for UART, that is TXDATA, RXDATA, TXCTRL, and RXCTRL. And we already enable the transmit and receive register. Now we have to deal with this other 2 register, that is TXDATA and RXDATA. So as this function we are writing, or we are transmitting some data, so we are only dealing with the TXDATA register. But for your lab, you have to do the data manipulation for RXDATA, because that's your task for lab 3. So yeah. So what we are doing, we are collecting the data from the TXDATA register, and we know how we are accessing the data from this TXDATA location, and dereferencing it and storing it to this register val. And we also know why we are using the volatile. Please, if you are not familiar with these terms, please revisit lab 2. That's gonna help you to understand if you don't know about these terms, like the keywords. So the thing we need to know here, that is how we are checking these conditions. Like, we know if inside of this while condition, if it is true, the loop will run forever. So while true, if it is true, then this loop will run forever. And if the condition is false inside this while loop, we are gonna break this loop, and we are gonna execute the next instruction or the next line of code, right? So what makes this value true or false? Now let's dig deeper. So as we can see here, we are doing an AND operation, and I want to tell you something. When we are doing the AND operation, the bitwise operation, if we do the operation 32-bit AND operation with 32-bit AND, it's a confused term. So if we do AND operation between 2 32-bit numbers, the output is gonna be also a 32-bit number. But if one of the number is just the 8-bit, the output will always follow the lower, the lower number of bits. So in that case, if our AND operation, if that one of the number is 32-bit and the another number is 8-bit, the output will always produce 8-bit. So as you can see here, we are doing some AND operation between register val and this fixed value. So this fixed value is nothing but is all zeros, 32-bit of zeros, except only the 31st bit is 1 if we start from 0. So the details of this operation you can see in this table. So before going into the details, I just want to let you know how we can read the data. I mean, how we can understand what data we need to make that operation. For example, for our TXDATA register, our 31st bit is a special bit that tells us if the FIFO is full or not. So here the FIFO is first in, first out, and it basically tells us if there is any data to transmit or not. So if there is some data in our data field inside of this register, then this bit is 1 because we have some data to transmit. If we have nothing inside of this data field, then this 31st bit is going to be empty, and the value of this 31st bits will be 0. So in summary, if 31st bit is 1, that means the transmit FIFO is full. If this 31st bit is 0 or false, that means the transmit FIFO is empty. We have nothing to send or transmit, right? So now it should be easier for you to understand that our register val have let's say 0 in 31st bit, and we are doing AND operation with 0x8 all the way to 0. And if we convert this hex number to binary, we get this value. So now you are observing that we are doing the AND operation, and somehow if this 31st bit is 0, it's gonna make the output 0, because that's how the AND gates works. Like if any of the input has 0, the output is always 0. So this while loop will immediately break if there is no data to transmit, and it will receive 1 if it is full. So if once we send the data to this data field, we'll observe this 31st bit value is gonna be 1. So if it is 1, and if we do this AND operation, 1 and 1 will produce 31st bit. I mean, the output is also 1. So it will eventually, continuously looping through unless all of the data, are transmitted. So, yep, I mean, that's in summary what this while loop is doing for us. So this basically is, in summary, this basically trying to say that if we have some data and we are not done with transmitting that data, we should wait. We should wait. We should wait if the FIFO is full. That means unless we transmit all the data, the 31st bit gonna be 1, and we are basically checking that condition if the FIFO is full or not. So now, if the FIFO is not full, that means in the 31st bit is 0, and we got 0 here, and the loop breaks. The next thing we are doing, now we know our data field is empty, and we can send our data to the data field. So as we know, we are sending, this function only taking 1 byte or 8 bit. So we are passing the data using a 8-bit manner. So after doing this, after executing this line of code, what we are going to observe in the TXDATA register, this 0 to 7 bits, we have all the ASCII values of C. And obviously, once we, fill some data on the data field, this 31st bit gonna be 1 as the data is full. We are ready to transmit the data. So this is the whole operation of how SAR write is doing. I hope you understand, and you have to implement your own SAR underscore read function, and please go through the lab manuals and try to complete the code. For the code, let's go over the code that you need to complete. So here we already write the serial write function for you, as you can see here, and you have to implement the serial read function here. So as you can see here, the serial read by we meant we want to read something from the UART, and we are trying to use whatever data we read and complete some certain tasks. So when we used the serial write function, we send some data to the TXDATA register to transmit. And now for serial read, as our goal is to collect the data from our computer's keyboard, that is when we are going to press, for example, R, it will simply send the ASCII character R through the RXDATA register. And next, we are gonna collect the data from the RXDATA register, and based on the data, if it is R, G, or B, we are gonna do some, GPIO write operation to blink the LED. So in this ECS38 underscore UART.c file, you can see here we are reading the character from serial read, and we're storing the character into variable C. And then based on the value of C, if it is R, G, or B, we are turning that LED on, right? So this part of code is already done for you. You don't have to do anything. You just need to modify or implement this serial read function. And please try to remember the serial read, so it's basically trying to wait for some data from the user. It is asking the user to press a button, either R, G, or B, right? So it will wait until the data it got, right? So that's why, as I already showed you in the table, the RXDATA register, this is RX control. So if you go to the lab manual, the document, you will have the similar RXDATA table for RXDATA register. For example, here, you can see this is the register of, this is the register RXDATA, and we have these fields. So as we know, from 0 to 7 is our data field, and we have a special bit that is 31st. And if the 31st bit is 1, that means the data field is empty. We have nothing. We didn't receive any data yet, right? So we have to implement a loop, a while loop, so that the while loop always wait. It continues looping forever until the user, pass some data to this data field, right? So the condition would be simply, we have to wait till the user pass some data through the keyboard. So once it got some data into the data field, this 31st bit gonna be empty, and for making this 31st bit will be full because previous it was empty. Now if it got some data from the user into this data field, this 31st bit is gonna be full. And for if the 31st bit is 0, that means the field is now not empty, it's full, and we are gonna just return that data from this field to our code. So yeah, it's pretty straightforward. So as you can see here, we are returning now we are returning only character R, but you have to return the data from RXDATA register, and you have to modify this return function. So I hope this helps you. This will help you to complete your lab. Thank you. I hope you understand the concept that UART.